Shooters, reloaders, and conversationalists, welcome to PounderLabs. 284 FClass Open Hoop Stress Study, Performance on the Edge. PounderPress is a research tool we developed by adding a precision force gauge onto a K&M precision arbor press. And in combination with Wilson seating dies, we're able to study the measurement of bullet seating forces. This creates a force versus time data stream, which we call a profile. This helps us get analytical results for bullet seatings and to further study our proposal for hoop stress as a replacement for neck tension. We also want to look more closely at other reloading factors. You can go to our website, which is linked over to these various videos that gives you more background information. You'll also notice in work in progress, we started talking about neck turning and tribology, and you can see some of our early efforts there. Before we get started, to make a point, we're going to borrow an idea from economics, and that's the returns curve, which looks something like this. This can be broken down into toe, rise, shoulder, and plateau. So the more effort you put into something, the more you get out of it, but at some point you start getting diminishing returns. We're interested in applying that to shooting because it gives us an amazing measure. Match results. So when you're looking at time, money, energy, learning into your shooting sports, you can expect to get better match results. Not just a single score, but consistency in matches and groups. So you can see that up here is a domain where you're going to start to win matches. So it's consistency that we're after. We want to make the point that our presentation today is really focused up in this region. So example, if you're in elementary school learning to play music, you probably don't have to worry about tuning a Stradivarius violin for a performance at Carnegie Hall. In high-performance shooting, neck turning is used for a couple of reasons. Adjust the neck to chamber design and dimensions, optimize concentricity, and leverage tribology factors. We were interested in this to study hoop stress as a function of wall thickness and also to understand neck tribology, smoothness, and lubrication. We found early on that we didn't have the equipment and skills to be able to move that forward. So we were very fortunate to work with Ray Branch, who's a noted FClass open shooter. And in one fell swoop, he has the tool and knows how to use it. He builds ammunition to the 99% performance range, and he has the firearms and knows how to use that. And most importantly, he's committed to perfection. So we're going to be focused on the 284 Winchester. We just call it the 284. And here you can see it compared to the 6.5 Creedmoor and the 308 Winchester. Here's an overview of the test bed and sight equipment. We're using a Bowman Custom 284 rifle. This is a documented sub-quarter MOA all the way out to 1,000 yards. This platform is built by Ray Bowman with Precision Rifle and Tool here in North Carolina. It's a Borden Rimrock action and a Bruex 32-inch barrel with the Bixen anti-ball bearing trigger. This is set in the Lowboy custom laminated wood stock. The Ray uses the March High Master 10-60. Notice the top end F-opened rest and bag. The lab radar for velocity data, the Kestrel for atmospherics, and copious notes in notebooks and logbooks. If we take a cross-section to the next section of a chamber, this is what we would see. The datum line, which sets the head space, and then the neck chamber itself, and then here we have the neck of the case. We call this the neck to chamber ratio, the gap in between here. What we're trying to do is get zero error alignment. From the model there, it looks simple, but in actual practice, it's much harder. The big problem is what do you use for rotation reference? Usually a traditional neck turning is done from the outside, so you use a pilot to support the inside of the neck while you're turning it. So more often than not, you end up with something like this, where the outside isn't concentric with the inside. So it begs the question, why not turn both the inside and outside at the same time? Well, that's not easy to do, and you need a tool designed to do this. Fortunately, recently FClassProducts has introduced the IDOD and the AutoDot, which does exactly this. Because of the phenomenal control Ray has over his reloading steps, we're hoping to run an experiment with varying just one factor, that's wall thickness. This would then be a simple full factorial design, varying the single factor, the other one's held constant. Here are the target wall thicknesses, first of all, as delivered and turning down to 6/1000ths. So this gives us 5 treatment combinations, level to the factor, 5 to 1, 5, 1, 2, 3, 4, 5. We're going to go with 5 shots per group size. This gives us replication. Normally in a laboratory, you run 3 replicates, you're usually in pretty good shape, but in shooting exports, we've learned that you really need to run a couple more. This will give us a good sample size statistically for calculating averages and standard deviation, and gives us good estimate of circular error probable. A note that the confounding factor, this ratio of neck to chamber, also changes, so we'll have to keep an eye on that as we move through the project. In experiments, such as we're doing here, turning necks, it's extremely important to have a reference, an anchor, if you will. So this is exactly what we have with Ray's round that he uses in matches. He uses 184 grain Berger F class, uses Lapua cases. Quick note, in this particular experiment, he has on hand a new lot of Norma cases, so that's what we're using in this particular experiment. He follows an 18-step case prep procedure, including neck turning with the IDOT, and then also neck surface polishing to further reduce asperities and neck lubrication. The load itself is 54.7 grains of 4831 shortcut. He does the bulk charge with the RCBS Charge Master, and then has a custom trickler to top that off, and uses a Sartorius lab balance. This is 1/10 of a milligram balance, which comes out to 2 milligrains for doing final loads. Here's a representative seating profile from our experiment, time versus seating force. Let's do a comparison. This is a 6.5 Creedmoor that's been properly annealed. So as we start to bring in the force, we first have a static portion up to about 31 pounds. The mouth opens, we get a force drop. This is the dynamic portion all the way up to about 98.5 pounds. The bearing surface goes past the neck and we get a drop down to FK, and this is where the drift bottoms out. Using the coefficient of sliding friction of 0.3, this gives us a hoot stress of about 7,400 psi. Here's an example using the 284. The wall thickness is 13.2. We can see that the mouth opens up down around 16 pounds. Very, very smooth, very, very flat through the dynamic section. And the bearing surface sits at the bottom of the neck, so we don't get a drop to FK. We did some dry seats to get that relationship, so that's why we know it's about 21 pounds. And then we hit the drift hits the bottom of the die. So again, using the coefficient of sliding friction, about 0.3, this gives us a hoop stress of about 2,200 psi. Note this is on the order of 1/3 of what we normally see seating a conventional round. When you first start seating a bullet, it takes a certain amount of force before the mouth of the case opens up. We call that the static drift force. This is a plot of that force as a function of wall thickness. The red diamonds are the raw data, the black circles the average for the group. And you can see as the neck wall gets thinner and thinner, it opens more easily and takes less and less force. But you get down to a point where the case wall is too thin. In this case, there's additional strain in the brass, creating more stress, and that force jumps up to do that. And you'll also notice the dispersion starts opening up. So we know that there's a limit down here to which you can introduce just so much stress into that seating before you start to run into problems. Let's now introduce the reference round and look closely at hoop stress. The chamber clearance is 316.6 thousandths. The round is 312 thousandths and gives us a wall thickness of 12.5 thousandths. The bump back is roughly nil, maybe a thousandth, but the critical jump is 20 to 22 thousandths. This is a plot of the hoop stress as a function of our wall thicknesses. As before, the diamonds are the raw data and the black circles are our average. And you can see as we start turning the wall thickness, we start to get a reduction of the stress in the brass. So we'll probably suggest this is the optimum range. Ray has been running right in this region right here already. But you'll notice now, even more so than with the static drift force, hoop stress is more sensitive and shows that strain coming into the brass. It's just getting too thin and the strain's there. And when we were firing these rounds, we thought they would actually split, but they didn't. So what we're suggesting is that for this load, hoop stress using the sliding coefficient of friction of 0.3, we want to target about 2,250 psi. Now we're at the range, ready to test our work. Calm day, the wind is virtually nil. It's a chilly day. We got pretty high barometric pressure, and speed of sound's in at 1,100 feet per second. We use 100 yards, 30 cinder block bench rest for calibration. Our rounds are shot group by, then going into a decreasing wall thickness. Let's watch Ray demonstrate excellent bench technique testing our samples. Ray would like us to share, and we wholeheartedly agree. Each rifle has a personality. You have to learn and understand what it likes and how to work with it. We call this tuning the rifle, and you're watching state of the art. We now have muzzle velocity as a function of wall thickness. The blue circles are group averages, and the red diamonds are standard deviation. From experience in matches, Ray knows he wants to be around 2,800 feet per second. We want to strive for standard deviations less than 10 feet per second. So we can see right in here would reach the optimum objectives, and we're going to see wall thickness between 10 and 12 thousandths to get there. We now revisit this idea of the confounding factor ratio of neck over chamber. Here we have the same plot as shown earlier, except now the ratio versus wall thickness. Up here you're virtually a slip fit into the chamber and it goes down. As you can see, we have the same characteristics as with the measurement of wall thickness. So we're at 98.5% with the wall thickness at 12.5. So we can say that the RNC tracks with wall thickness and that it doesn't adversely affect performance. Now we turn our attention for hits on targets. These are the target workups for the best wall thickness at 10.5 thousandths and the worst at 7.8 thousandths. The standard deviations in X and Y in both are fairly symmetric, so we're not getting any windage effects or getting any kind of stringing from barrel heating and such. To the untrained eye, this might not look like much difference, but when you look at the statistics, in this case the circular air probable at 0.138 inches compared to 0.230, this CEP is half of what it is over here. So we can see that there's been a pretty significant change in the performance with hits on targets with reducing neck wall. Now we can add hits on target performance data to our reference load. This is everything we've learned to this point, and we can look at the plot of CEP versus wall thickness, and by turning down to about 10 to 11 thousandths, we can expect a 100-yard group size reference CEP less than 0.2 inch. We continue to hold that hoop stress is a better measure for bullet seating than the traditional notion of neck tension, which wasn't used in this project at all. It brings out the best in the available high-quality reloading tools and methods that we use, and it gives us new insights into case bullet service tribology. For the F-class open shooter, it helps discover the best wall thickness, what's the optimum for that. We've demonstrated that the IDOD and the AutoDot is a valuable tool for the precision reloader, and it helps further correlate velocities and hit on target analysis. And the work also helps inform the next design of the firearm, giving more insights there. It's another example of applying analytics to what we already work with in shooting. Gives us new insight and faster time to solution. You'll notice that in this design we actually use less than 30 rounds. So I think it's a very efficient way to get to solutions. And then we've helped validate Ray's case prep and load development techniques. We would like to extend a very special thanks to Ray. We can say categorically that this project would have been impossible without his skills and commitment to the project. To learn more about F-class competition, you can start with this article here. If you're looking for precision rifle builds in several different categories, visit the folks at Precision Rifle and Tool. If you're interested in the neck turning tools, visit F-class website here, as well as several other products that they offer for the F-class shooter. This completes our presentation. And as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. Be safe. See you soon.